Through this video, we would like to present the crucial role of space telescopes in the field of multi-wavelength astronomy, a discipline that enables us to observe the universe in a spectrum of energies, from radio waves to gamma rays. But before we venture beyond Earth's atmosphere, let's begin our journey where astronomy first took a major leap, with the advent of ground-based telescopes. The first recorded use of a telescope to observe the sky by Galileo Galilei transformed humanity's perception of the cosmos. With a simple tube fitted with lenses, he revealed mountains on the moon, moons orbiting Jupiter, and countless unseen stars. His observations shattered age-old beliefs and initiated the era of modern observational astronomy. Over the centuries, ground-based telescopes have grown in scale and sophistication. From small refractors to giant optical observatories perched on mountaintops, they have helped us uncover new details about our solar system, mapping planets, moons, and asteroids with increasing precision. They have also played a vital role in detecting exoplanets, observing stellar nurseries, and measuring cosmic expansion. With radio telescopes, we have probed the coldest and most distant corners of the universe, and thanks to enormous mirrors and adaptive optics, astronomers now peer deeper into space than ever before. Our view has expanded dramatically, from studying our local neighborhood to mapping the distribution of galaxies across the observable universe. Yet despite these remarkable achievements, Earth's atmosphere imposes limits. It blocks or distorts much of the electromagnetic spectrum, preventing us from accessing vital information encoded in different wavelengths. This brings us to a fundamental question: why is there a need to put telescopes in space? The next segment will explain the critical relevance of space-based observatories and how they complement ground-based instruments. By placing telescopes above the atmosphere, we unlock a clearer and more complete view of the universe. Multi-wavelength astronomy allows us to study celestial objects across the electromagnetic spectrum, each wavelength revealing a different layer of physical processes. Take the Crab Nebula, for example, a pulsar wind nebula located in the constellation Taurus. When viewed in visible light, it shows a delicate filamentary structure. In infrared, it exposes cooler dust and gas. In X-rays, it reveals the energetic processes powered by a rapidly spinning neutron star at its core. Gamma-ray observations expose even more extreme activity. Together, these wavelengths provide a holistic picture of the life cycle of a star that ended in a spectacular supernova. India too has contributed significantly to this field. Our country now operates space-based telescopes that observe the universe in UV, X-ray, and visible wavelengths. Let's take a closer look at them. One of India's most recent achievements in solar science is the Aditya L1 mission, launched by ISRO on September 2, 2023. The spacecraft is positioned around Lagrangian point 1, a gravitationally stable location approximately 1.5 million kilometers from Earth. From this vantage point, it enjoys an uninterrupted view of the Sun, crucial for continuous solar monitoring. Among its suite of instruments is SUIT, the Solar Ultraviolet Imaging Telescope. SUIT is one of Aditya L1's primary payloads, designed to observe the Sun through multiple ultraviolet filters. These UV observations are essential because they originate from layers of the Sun that remain invisible to the naked eye yet play a key role in driving solar activity. Across the world, numerous missions have studied the Sun, each focusing on specific layers. Some capture the outermost and extremely hot solar corona, where temperatures soar to several million degrees. Others focus on the photosphere, the visible surface of the Sun, where sunspots and magnetic features emerge. What sets SUIT apart is its ability to serve as a bridge between these layers. By capturing ultraviolet images from the regions sandwiched between the photosphere and corona, it helps us understand how energy and magnetic fields propagate through the solar atmosphere. This offers a more complete, almost three-dimensional perspective of dynamic solar events, such as solar flares, active regions, and coronal mass ejections, CMEs. These are not just fascinating phenomena, they can also impact Earth's magnetosphere, affecting satellites, communication systems, and power grids. Thus, instruments like SOOT play a crucial role in advancing space weather forecasting. Another landmark mission from India is AstroSat, launched on September 28, 2015. It recently marked a milestone, completing 10 successful years of service. AstroSat is often referred to as India's first dedicated multi-wavelength astronomy observatory.
It was a huge day for Indian astronomy on 28 September 2015 when AstroSat was launched. It was India's first observatory in space. Normally we have telescopes on land which are easier to build. However, most of the high frequency light is stopped by our atmosphere and it is great for living beings on Earth, otherwise we will all die due to radiation exposure. But not so good for the astronomers. And so to study high energy radiation emitted in space, we need to have an observatory and telescopes in space. AstroSat was placed in orbit by PSLV XL C30, a 4-stage rocket with 6 strap-on motors. PSLV weighed 320 tons and it was as high as a 15-storied building.
The satellite itself weighs 1.5 tons, equivalent to the weight of a car, and is 2 meters in height.
And so to put 1 kg in orbit, we need 150 kg of rocket and fuel. At 7.5 kilometers per second, AstroSat is 200 times faster than Shatabdi Express, the fastest train in India. The stages of PSLV keep dropping at different heights, and finally the 4th stage rocket delivers it in almost circular orbit. The orbit is almost parallel to the equator, inclined at an angle of 6 degrees. At its speed, AstroSat goes around the Earth every 97 minutes or 15 times a day.
AstroSat's orbit is 99% circular, with just 1% elliptical eccentricity. This was done by achieving a precise rocket speed, such that the gravitational force of Earth is equaled by the centrifugal force. If the speed is more, the orbit will become more and more elliptical till the AstroSat escapes the gravity of Earth and flies away in space.
AstroSat is powered by solar panels providing 1.5 kilowatt of power. This is the same power as a geyser we use in our bathrooms.
AstroSat has an antenna operating at 8 GHz band and transmitting data at 105 megabits per second. Whenever it passes over the 2 receivers at ISSDC Bailalu near Bangalore, we can send commands to AstroSat and receive data that AstroSat has collected. The contact remains alive for about 3 minutes, and so the total data that can be received is about 4.7 gigabytes, the size of a full HD movie.
We spent 178 crore rupees on AstroSat, excluding the cost of delivery. Is it worth it? Well, you decide. If something is wrong with our bodies, doctors use various cameras, ultrasound, X-ray, infrared, by which they can get the correct picture of our body. Similarly, to find out what is going on in the universe, we need to look at the light emitted by objects. The objects emit light not just in visible range, but in gamma rays, X-rays to ultraviolet, visible, infrared to microwaves and radio waves. So to observe all these radiations, we need different telescopes in space. And this is what AstroSat, with its 5 cameras bundled in one, does for us. The 5 cameras are UVIT, LAXPC, SXT, CZTI, SSM. These cameras provide information regarding the binary star system, neutron stars, black holes, star birth regions, etc. And if we think about money, we anyways burn crackers worth 10,000 crores every Diwali.
AstroSat is the culmination of painstaking years of work of scientists from 6 premier Indian institutes: ISRO, TIFR, IIA, PRL, RRI, and IUCA.
The analysis and discoveries are to follow when AstroSat starts delivering data in 6 months.
And so we look forward to enhancing our knowledge about space, wonderful discoveries, and great science with the help of data received from AstroSat.
Together, space-based observatories such as Aditya L1 and AstroSat demonstrate India's growing capability in astrophysics and space science. They not only complement global missions, but also enable us to explore the universe from entirely new perspectives. As we continue to develop advanced instruments and explore fresh wavelengths, multi-wavelength astronomy will unlock deeper insights into the origins, evolution, and mysteries of the cosmos. The journey continues, and each mission brings us one step closer to understanding our place in the universe. Now, let's move our attention to the NASA Voyager mission. In 1977, humanity launched 2 spacecraft on a mission to explore the outer planets of our solar system. The Voyager mission was planned to take advantage of a rare 176-year alignment of the outer gas giant planets in the solar system, like Jupiter, Saturn, Uranus, Neptune, in the late 1970s to perform a grand tour using gravity assist maneuvers. This would reduce the travel time to Neptune from 30 years to 12. These spacecraft were called Voyager 1 and Voyager 2. Their mission was supposed to last just a few years, but nearly 50 years later, they are still traveling, and they are farther than any human-made object has ever gone. Today, they are exploring interstellar space and giving us information about what is beyond the boundary of the solar system. Each Voyager spacecraft carries a golden record. This record contains sounds and music from Earth. It includes greetings in 55 languages. It also contains images of humans, animals, and our planet. It is a message from humanity to any intelligent life that may find it in the future. It is like a message in a bottle, sent into the cosmic ocean. During its journey towards the outer solar system planets, Voyagers made many incredible discoveries. It found giant storms on Jupiter, including the Great Red Spot. They revealed the beautiful rings of Saturn in stunning detail. But Voyager 2 became the only spacecraft in history to visit Uranus and Neptune, as Voyager 1 was on a slightly different trajectory. They also discovered new moons, new rings, and active volcanoes on Jupiter's moon Io. These discoveries completely changed our understanding of the solar system. In 1990, Voyager 1 did something extraordinary. It turned its camera back towards Earth when it was close to Saturn and took one final photograph. In that image, Earth appeared as a tiny dot. This famous image is called the pale blue dot. That tiny dot is our home, where we all live, and the only place in universe we know where life exists as of now. It reminds us how small and precious Earth is in the vast universe. We must preserve and care for our Earth. Let's end this video by turning our attention to another recent big achievement by Indian astronomers, the Alaknanda galaxy. Alaknanda is a grand design spiral galaxy, meaning it has a clearly defined shape with two symmetrical spiral arms and a central bulge. It looks strikingly similar to our own galaxy, the Milky Way, despite existing in the very distant past. The galaxy was named Alaknanda after the Himalayan river. The astronomers chose this name because the Alaknanda river is a sister headstream to the Mandakini river. Since Mandakini is the Hindi name for the Milky Way, the name poetically suggests this galaxy is a distant sister to our own. We are seeing this galaxy as it existed just 1.5 billion years after the Big Bang, roughly 12 billion years ago. In cosmic terms, this is the toddler stage of the universe, yet Alaknanda appears fully grown up and structured. According to standard theories, the early universe was a chaotic, hot and messy place, where galaxies were clumpy and irregular. Well-ordered spiral galaxies were thought to take billions of years to settle down, making Alaknanda's existence this early a major challenge to current scientific models. Despite its orderly appearance, Alaknanda is incredibly active. It is churning out new stars at a rate of roughly 63 solar masses per year, which is nearly 20 to 30 times faster than the star formation rate of our current Milky Way. The galaxy is so far away that even the James Webb Space Telescope, JWST, needed help to see it clearly. Astronomers utilized a phenomenon called gravitational lensing, where the gravity of a massive cluster of galaxies in the foreground acted like giant lens, magnifying Alaknanda and making it appear twice as bright. The discovery was made by two Indian astronomers, Rashi Jain and Professor Yogesh Vadadekar, from the National Centre for Radio Astronomy NCRA-TIFR in Pune. They identified this unique object by combing through publicly available data from the JWST. This discovery suggests that the universe was capable of building complex, stable structures much faster than previously believed. It indicates that the physical processes that create orderly galaxies can fast-track evolution, forcing scientists to rethink the timeline of how the cosmos developed.